right? So it doesn't take, notice that, it doesn't take an equal amount of time. So as you're approaching, the amount of time is starting to increase, okay? Because as you're approaching, you have to think about this graphically. The graph of the total energy looks like this, right? You have to think of it graphically like that. So if you are losing an equal amount of increment of energy per day, so let's say equal amount of, let's say my increment is this, my increment is this, my increment is this, so let's say this is the increments here. Okay, so let's say I started out a certain orbit, a distance d away, right? So this is the total energy graph. So it's always good to also look at what you're doing, the numbers you're getting, is it making sense, make sense out of them. Everything is graphical, visual, not just mathematics, you know. So if I'm losing a certain amount of energy, I'm essentially going down the energy path, you see? So initially, if I lose a certain amount of energy, I lose a lot of distance. Notice this distance here? That's the distance that you lose. Then you lose a little bit more energy. The next increment of distance you lose is not as much. Then you lose another energy. The next distance you lose is not as much. Then you lose an equal amount of energy. Then you don't lose as much. Then you don't lose as much, so on, so on, so on, you see? So equal amounts of energy loss are not affecting the distance d as much, okay? Because as you're spiraling inward, your potential energy is getting more and more and more lower. It's getting steeper on the graph path, okay? Okay, so that's good. Why don't we answer this kind of a question? The next thing that we had done on that problem is we had said, if somebody is at the surface of the Earth, how fast would the Earth have to spin in order to not retain that person, okay? So we applied circular motion to gravity and set the normal force equal to 0. Let's add a part E to that problem and say, how fast would a rocket on the Earth have to be in order to be sent out to that geosynchronous orbit? So how fast would a rocket have to be launched to go to geosynchronous orbit? So that's kind of related to what we've been doing. So if we wanted to send the rocket there, how much velocity should we have to give that? Now the answer we get should be quite less than the escape velocity from the Earth. The escape velocity from the Earth is how much you need to go to completely escape from the Earth, right? So if we escape, remember to calculate the escape velocity, you do square root of 2gm over the radius of the Earth. Or if you were on the sun, you would do the mass of the sun over the radius of the sun. So if you apply that equation to the Earth, the escape velocity of the Earth comes out to be roughly of the order of 29 kilometers per second. I believe I might have mentioned this earlier when I did that problem earlier for binary stars. Okay? So that's 29 kilometers per second. So the velocity we get now should be quite less than that because we're not trying to escape, we're trying to just go to geosynchronous orbit. So how would we get that? So we would say kinetic initial plus potential initial is equal to kinetic final plus potential final. Okay? So then you would say kinetic initial is half mv initial squared. Potential initial is negative g mass of the Earth and then the mass of the satellite divided by the radius of the Earth, and then the kinetic final plus potential final, well, that's equal to the total energy that the satellite will have by the time it goes there, right? So that's just simply negative gm little m over 2d. Right? So in order to get the velocity, we just take this over there, so for v. Now notice the mass little m is going to cancel, so the answer that we get will be independent of the mass m of the rocket. Okay? So we have here half v initial squared. This one goes over to the other side, and then I can factor out the gme. Okay? Then I'll be left with 1 over radius of the Earth minus 1 over, so I have 1 over radius of Earth, and then 1 over 2d. Remember, I can't forget the 2, so I don't want to make the same mistake. And then I have 2d here. So then I can put in everything. The initial squared is equal to 2gme 1 over re minus 1 over 2d. And then I can square root this thing, huh? Now notice here, if I set d go to infinity, and limit as d goes to infinity, well, what do I have? I have the escape velocity equation. The escape 2gme over re. And we're back to ground zero. That's the equation for escape velocity. Okay, so let's put in all the numbers, calculate this, and then we'll be done with that problem. So V initial needs to equal square root of 2 times G is equal to 6.673 times 10 to the minus 11. Mass of the Earth is equal to 5.974 times 10 to the 24th. Times 1 over radius of the Earth, and I have to change this to all the answers to meters. So the radius of the Earth, we've been using the average radius of the Earth, which is 6,378 kilometers. So 6,378 kilometers, but then I have to change it to meters, minus 1 over 2 times the distance d, which had come out to be 42,242. 42,242.67. 42,242.67, and then that's 10 to the third. 378. So I get a pretty small number, of course. Then I'm going to multiply this. Well, this one came out to the outside. I'm going to multiply this by 5.974. I'm going to multiply it by 2. The answer, I multiply this by whatever answer this gave me. And then my final answer is 10,000. Let's see. If I change it to kilometers per second, so that I can compare it to the escape velocity, I'm going to get 10.75 kilometers per second, and that's our final answer. So notice it is a lot slower than the escape velocity, which is 29 kilometers per second. So I only need to do 10.75 kilometers per second in order to go out to geosynchronous orbit. If I wanted to go out farther, I would have to give more velocity. If I wanted to go less than geosynchronous, I would have to give less velocity. Okay.